Today we're going to talk about different kinds of models that you can use in mathematics, and basically all that really means is using math to describe something that's going on. So for the last few days we've been talking about exponential models, meaning that you have a number to a power. So an exponential equation is one in which you have y equals a number to some kind of x thing. For example, maybe like y equals e to the x. Remember, e is an irrational number. We've also talked about logarithmic. Equations like y equals the log, there's some number here, and then an x. Oftentimes we'll do something like y equals natural log of x. That has a base of e as well. And we use e often because we find that e pertains to a lot of things in our world. And so what you'll notice is when they talk about these models, they have different kinds of exponentials. So here's an exponential that's growing on the left-hand side. You can see it's going up. That happens when the number that's associated with the power is positive. That's why it's going up. So if you have e, like for example, y equals e to the 3x. The power is positive, it's going up. In the second example, if you look at it, what you'll notice is that the graph is going down. This is also an exponential model, but it's called exponential decay because it's going down. That happens when you have a negative power, like e to the negative 3x. So if the power is positive, that's what this b thing is saying right here on the left in the dark blue. And this b is talking about if the power is negative. And so these models that you see down below, in our class, the top two, the exponential ones, are ones that we've talked about a bit. The next couple you're not really going to talk about. One's called the Gaussian model. Friedrich Gauss was a famous math person who discovered some things. And then there's a logistic growth model in number 4. Logistic growth you'll use in calculus. So we're not really going to talk about logistic growth or the Gaussian method too much. And this is in calc. You'll talk about this model a little bit. It actually happens in our world often. If you know anything about hunting or fishing or anything to do with populations of animals, what you'll realize if you've taken any classes about this or read a little bit about it is things change based on population. So for example, the wolf population in Minnesota is really large right now, and they're offering a permit to hunt wolves, and they're fighting it right now in the courts. And the reason they're doing that is because there's a lot of wolves. And the reason there are a lot of wolves is because for the last few years, the deer population has been really large. A lot of production of deer. And so when the food source goes up, so do the predators, because the predators get to eat. And so what ends up happening is you'll see a model where the wolf population will grow and grow and grow and grow, and then all of a sudden it'll start to dip, and then it'll grow, and then it'll dip, and then it'll grow. And what you'll find out is there's something called a carrying capacity, or a limit really, to the wolf population. And that's where you see, like in the logistic growth model, you see the line level out over time. And that's what logistic growth is talking about, is your equilibrium, or your leveling out, or your limit. And so this line that you see going off to the right here is talking about what would you expect the population to stabilize at. So that's kind of a practical application of what logistic growth is doing. We're not really going to talk about that in here either. And then we also talked quite a bit about logarithms. And logarithms are, remember, the inverses of exponentials. And you can see that if you were to draw the line y equals x, and you could reflect the exponential model over that line and see the logistic growth, or not logistic, excuse me, the logarithmic growth, and see what's going on. So really what we're going to talk about today are numbers 1 and 2, which are really the same graph. One's going up, one's going down, one's growing, one's decaying. They're both called exponentials. And then the logarithmic graph. So those are kind of the two main topics of today. There are 6 example problems in our notes today. We're only doing 4 of them. Okay, and then we're done. So let's try one. Example number 1. We have a population, and we have a certain model. You'll notice it's an exponential model. The base is e. X equals 0 is talking about 1990. Now, this is kind of important because people mess stuff up all the time because they're not paying attention to the words. So you need to know x0 is 90. And they want to know, when is this thing going to reach 2.5 million? So the way you start out this problem is you set the 2.5 million for the population equal to your equation, 1.8 e to the 0.026x. Now, I'm not going to do this because I assume that all of you know how to do this. I'm going to talk about it, and then I'm going to do it algebraically. But you can always solve these equation things on your calculator. It's a great tool. So if you were going to do that, what you would do is you would put the left-hand side in y1, put the right-hand side in y2, second trace 5, enter, enter, arrow, enter. We've done that in our class a lot. We'll continue to do that in our class a lot. And then you'd find whatever the x is. That's it. That's how you do that. I'm not going to do that. What I'm going to do instead is I'm going to use the algebra because I figure that's where most people need a little bit of help just in case it ever shows up that way. So I'm going to divide both sides by 1.8. If you divide both sides by 1.8, I have no idea what that is. Anybody have any idea? Is it a long decimal, short decimal?
1.3.
Exactly?
Repeating.
Forget it. Okay, so I'm just going to write down this is how great math is when you only have to use your calculator once. So I'm going to do 2.5 over 1.8 equals e to the 0.026x. Remember, our goal is to find out what the x is. Crap, it's in the power. I need to get it out of the power, so I ln. I natural log both sides. The reason I'm natural logging both sides is the natural log and the e are inverses of each other. So we know that these things will undo each other. So now I really have that the natural log of 2.5 all over 1.8 is equal to 0.026x. And I want to find out what my x is, so I really only have one more step left. All I have to do is divide both sides by 0.026. And when you do that on your calculator, try it now, you should get 12.635. Don't forget that this 12.635 is in years, because you're trying to figure out when is this going to happen. But that's not how they want their answer. They want to know what year. So if you're in January of, what was the year? 1990. And 12 years have gone by, you're now in January of 90 to 91, 91 to 92, 92 to 93, 93 to 94, 94 to 95, 95 to 96, 96 to 97, 97 to 98, 99 to 2000, 2000 to 2001, that's 10 years, 2001 to 2002, 2002 to 2003. You're now in January of 2003. Crazy. And then what does the 0.635 mean? About 7 months. If that doesn't make sense to you, feel free to write out a timeline and count out the number of years. It may help. Make sure you answer the question. The question was, what year? So that's why I was responding with the year. If you wrote down 12.635, you get all but 1 point on the exam. So make sure you know what it's asking. Oh! Number 2, cross it off. Number 3. In number 3, they talk about a radioactive material. radium, for any of you who are in chemistry. It has a half-life of 1,620 years. The original amount is 5 grams, and they want to know how much is left after 10,000 years. And half-life means how much goes by for half of it to remain. So what I want to point out is, here's what I know. I know that if something is what they call exponential decay, like whenever they talk about half-life, this is talking about exponential decay. So one of our original graphs, one of the 3 that we said we would be talking about, it's the exponential one that's going down like this. This is exponential decay. And so because it's exponential decay, the formula that we use kind of looks like our PERT equation, maybe for the lack of a better way to say it. So we know that like the amount was equal to the principal e to the r times t. And that's usually the way they write it when you're talking about money. And when you're talking about things like bacteria growth or things like that, they change some letters, but really it works exactly the same way. So when they're talking about things like exponential decay with radioactive material, oftentimes they'll write down the amount is equal to, and I don't know why they do this, but they put a c e to the kt. And what you'll notice is they're really exactly the same. Instead of having a rate, they have a k. They call that the constant of decay. The c is the initial amount that you started with, and the a is the amount that you end up with. So based on what they told me in the sentence, something I know is, if I start out with 5 grams, then after 1,620 years, I will end up with half of that, which would be 2.5 grams. And I can't forget that I also have an E here and a K. Bless you. Why am I writing this down? What is this going to do for me? Sam?
You'll find the rate of decay.
That's right. I'll find the rate. The constant, the rate constant. Not the amount of years it takes to decay, but the rate that goes along with it. So I'm going to do that next. I'm going to find that K thing, because otherwise I can't solve what I'm actually looking for. I need to find the K first. So there's actually 2 separate problems going on here. Find the K first, and then do the problem they're actually asking you for. Divide both sides by 5, and oh look, I get 1/2, because 2.5 over 5 is 1/2. So whenever you see half-life, you could always start out with half, if you want. Equals e to the 1,620 k. Darn it, there's an e.
ln.
ln. So let's ln it. I take the natural log of both sides, and I end up with the natural log of 1/2, which I have no idea what that is. We don't need to worry about it right now. Equals 1,620 k. So to get my k, all I would have to do is divide both sides by 1,620. So then my k, or my constant that I'm looking for, turns out to be negative, try it on your calculator, 0.000428. Now what I want you to do is, if you ever do one of these half-life problems, I want you to find that constant to 3 decimal places after the zeros. So notice how I have 3 zeros, that doesn't count as 3 decimal places. So in this case I had to go 6 to get there. If there were 5 zeros, then you'd have to go 8. Make sure you have at least 3 non-zeros after the zeros stop. Okay, that's kind of important. So here's my k. I'm going to come back to that. The question says, how much is going to be there after 10,000 years? So now what I do is I'm like, okay, I know I'm going to start out with 5 grams. And it's e to the, I know that my k is negative 0.000428, and that's getting multiplied by the 1620. This is the question that they're actually asking me.